let's do a problem about some basic probability concepts with M&Ms. This is from chapter 14 of Bach, Bellman, and DeVoe. So it used to be, this is old information, but let's just say that M&Ms come with 20% of them being yellow, 20% being red, 10% for each of orange, blue, and green, and some unknown percentage for being brown. And we're going to figure that out in a minute. And the first thing to ask, good question to ask first, if you pick one M&M at random, what are various probabilities? What's the probability that it's brown, yellow or orange, green, or striped? Striped, interesting. It's not my question, it's the book's question. So what's the probability that it's brown? Well, unfortunately, that's exactly the information they didn't give us. But we can use some of the basic ideas of probability, or just really common sense. It's all the leftover. So you could say, well, we're just going to calculate the percentage in the population that's brown, and then use that. That's certainly one way to do it. So we have 20 plus 20 is 40, plus another 30 is 70. So it looks like there's going to be 30% here that are going to be brown. Or a more sophisticated way of saying, and you don't have to do it this way, but it's good to get practice with these kinds of concepts, is that the probability of brown, it doesn't like it when I do math mode for words, is 1 minus the probability of all the rest. That's the complement principle. And then the another important principle comes in. It can't both be yellow and red, or both red and orange. And in fact, our calculation before would not have been correct if it could be simultaneously yellow and red, or orange and blue. Then we couldn't just add these up and take 100% minus that. Okay, so we really were using this principle in that, even in that version of the calculation. It's the principle that these are all disjoint events. Okay, so let me put a little note. Disjoint, or another phrase is mutually exclusive, that they exclude each other. If you know it's yellow, that excludes the probability of or the possibility of it being red. Okay, so we could do it in equations as this: yellow, or, and the or is the little union symbol, red, or orange, or blue, or green. Okay, and that, of course, is 0.3 or 30%. Okay, so we've really used an important principle here, the disjointness of these possibilities. Okay, if this was a table of people and this says man, woman, lawyer, doctor, you couldn't add up all these things and take 1 minus that to get another probability. Wouldn't work. Okay. Well, what's the probability that it's yellow or orange? So here again, we've got an or, and it's really crucial that you can only add probabilities in a simple way for the or statement if they're mutually exclusive. But they are. There's no M&Ms that are both yellow and orange. So the probability of yellow or, that's the union symbol, orange, that's the simple addition rule, and that is the probability of yellow, that's not how you spell that, plus the probability, I'm getting confused, of orange, and that's going to be 0.20, I can leave that in math mode, thank you very much, plus 0.10, so that's another 0.30, or 30%. Okay, and again, we can only use the simple addition rule, only works when these are disjoint or mutually exclusive, but they are. Okay, what's the probability that it's not green? That's the complement principle. Probability of not green, I guess I've been capitalizing my colors for no particularly good reason. Well, that's again very similar to what we did here. It's 1 minus the probability that it's green. And that's easy. That's just 90%. 0.90 or 90%. And the probability that it's striped, well, I think they're just being funny there, but the probability of striped, of course, anything that's impossible, I think they're trying to just get across the point that you can ask those kinds of questions, and they have a definite answer. They just have a particularly simple answer. The probability of striped is 0. That just means it's impossible. Okay. If you pick 3 M&Ms in a row, now it gets a bit more interesting, not just one M&M. What's the probability that they are all brown? Okay. Now this is actually a little trickier than they're letting on here. Okay. Suppose I just have a batch, a very small batch of M&Ms, like 10 M&Ms. And there's 2 yellow, 2 red, 1 orange, 1 blue, 1 green, and 3 brown. If it's a small batch, then this isn't a well-defined question. They really need to tell you with replacement or without replacement. If it's a huge bunch of M&Ms, it's a really big bag, then it doesn't really matter, because picking out 1 or 2 or 3 M&Ms isn't going to matter very much in terms of what's left. But if it's a small number of M&Ms, picking them out without replacement is going to affect these probabilities. Okay, so even if you start with exactly these percentages in the bag, then if you pick without replacement, it's going to be complicated. So what we're going to do is we're going to assume that the bag has these exact percentages in to start with, that those are accurate, and then we're going to actually pick them with replacement, which is sad because that means we can't eat them as we go. But then maybe we'll eat them later. Okay, so we're going to pick one, put it back, pick another one, put it back, or we're going to assume a really big bag, in which case these probabilities, these percentages, don't change appreciably when they come out. But it's not a very well phrased question, because they should always be getting you to think about this. Okay, so let's assume that we do it that way. What's the probability that they're all brown? Well, that's an and. That's the probability that the first is brown, and we use the intersect symbol. The second is brown, and the third is brown. Okay, and when you do it with replacement, or it's a really big bag, that's essentially assuming that these are independent events. That just because I got the first one brown doesn't decrease the probability of getting a brown in the next pick. If it's only 10 M&Ms, that's completely wrong. And so it's really important that either you replace that brown M&M so the probabilities are not changed, so they are independent, or it's just a really big bag and you're not making a big difference. Okay, given that we have the independence assumption, we have a wonderful principle, which is it's just the probability of the first one is brown times the second one is brown times the third one is brown. And we're assuming that those aren't changing. And so it's just the probability of brown times itself 3 times, or cubed. So that's 0.3 cubed, and that is 0.027. Okay, so it's a pretty small probability, about 2.7%. Even though browns are the biggest percentage, getting 3 in a row is not that likely. Okay. Let's see here. Something seemed weird. No, that's right. Okay. The third one, what's the probability that the third one is the first one that is red? Okay. Well, let's see. We need to phrase that in terms of ors and ands. We want to make sure that the first one is not red. And we want to make sure that the second one, oops, not a union, it's an intersect, it's an and. Second one, not red. And the third one is red. Okay. Now again, we have to assume this assumption, the independence assumption. But if we do, then we just have the product of the probabilities. The first not being red is 80%, because there's a 20% to be red. Okay, so that's an 80% for this one, times, that's using the independence. Second not being red is another 80%, 0.8 probability, and then times a 0.2, because on the third one we actually do want it to be red. Okay, and let's see, that's going to be like 0.128, I think, right? Yeah, equals 0.128, or 12.8%. Okay, so that's actually, it's actually fairly likely. It's interesting that it's more likely than getting 3 browns, mainly because the first 2 conditions are just saying not red, which is actually pretty darn likely. Okay, what is the probability that none are yellow? So that's interesting. None are yellow means the first one is something besides, the second one is something besides, the third one is something besides. Whenever you have a condition of like none or at least one, you might want to start thinking about complements, things like that. So the probability that none are yellow, we could think about yellow, or we could think about all the others. It's really that I want the first one to be anything but yellow, and the second one to be anything but yellow, and the third one to be anything but yellow. Okay, so that's one way to think about it. What you don't want to do is it's easy to get confused about negations here. Well, let me do it a good way, and then I'll maybe talk about maybe confusions. So what's the probability that none are yellow? It's going to be, let me actually just copy this. First, not yellow. Whoa, I just did something really weird. No, I think I just scrolled into somewhere. And second, not yellow. And the third, not yellow. So it actually turns out to be very similar to the first one. And again, we're assuming these are identical and independent. And so the not yellow percentage was 80%. So 0.080 times 0.80 times 0.80. Okay. And that is 0.512, I think. 51.2%. I think that's right. Yep. Okay. So it's important that none being yellow is different from just that not all are yellow. So you could mistakenly do the probability of, I would figure out the probability that they're all yellow and then just take the complement of that. We really need to take the complement on each M&M. The first one is not yellow. That's the 80%. That's a complement. Second one, that's a complement, 80%. Third one, that's a complement. And then we multiply them together using the independence assumption. It's definitely not the same. Let me just write this out. Not the same as the probability of let's see, 1 minus the probability of all yellow, which would be 1 minus, and all yellow would be 0.2 times 0.2 times 0.2. And that's a very different probability. That's 1 minus 0.008. And that's a very large probability. It's 99.2%. Okay, totally different. It's very unlikely to get all yellow. And if you look at it's saying I don't get all yellow, that's almost all the time you're not going to get all yellow. But the probability that none are yellow is very different, and that's about half. Okay, so it's very important to be careful with the logic of these things. What's the probability that at least one is green? Well, at least one is almost always a marker for the complement, but this is about the complement on all of them. So at least one is green. The probability that at least one green, that's the statement that it's not the case that all of them are not green. Okay, so that's 1 minus the probability of all not green. So think about that for a second. At least getting at least one green M&M is exactly the negation of the statement that I didn't get any greens. Okay, and I know how to do that. That's exactly the kind of statement I had up here, the none are yellow. So 1 minus, so all not green is going to be, the first one's not green, that's 90%, and the second one's not green, that's 90%, and the third one's not green, that's 90%. Okay, and then that is, I can do that. That's 1 minus 0.729, and that's 27.1%. Okay, so about a quarter of the time you're going to get at least one green, because that's the negation or the complement of that they're all non-green, and that you can get by the process we got here. So this is getting pretty sophisticated in terms of the basic probability rules. We're using independence, the multiplication, we're using complements, putting events together. If you can get to this stage, you've got a really good grasp of the basics. Now, a couple problems later, they try to get us clarified on some of the things that I've already mentioned here. Disjoint, independent, what's the similarities, what's the differences? They ask, if you draw one M&M, just one, are the events of getting a red one and getting an orange one disjoint, independent, or neither? We've actually used this, very importantly. We used the fact that it was disjoint, or in other words, another name for that I often say, it's in a lot of books, mutually exclusive. If you get a red one, it can't simultaneously be orange, and vice versa. That's why these probabilities, these percentages, had to add up to 100%, because there's no overlap. Okay, so we can say no overlap in terms of the Venn diagram. Are they independent? Okay. If I know that I've got a red M&M in my hand, does that change the probability of whether it's orange? Well, absolutely. If I didn't know it was red, the probability of being orange would be 10%. If I know it's red, then the probability goes down to 0. So it's definitely not independent. Disjoint or mutually exclusive can never be independent. And in fact, they ask that down here, and we might as well skip to that. Okay, never, ever, ever. Disjoint events always change. Let me say it this way: with two disjoint events, knowing the truth of one, that one happened, always changes the probability of the other, namely to 0. That's the most drastic effect you can have on a probability, is setting it to 0. So this is never, ever, ever. These things are often confused. They seem sort of similar. They're not. They really, really are different. Okay. So here it was disjoint was the answer, and definitely not independent. Now, if you draw two M&Ms, one after the other, are the events of getting a red on the first and a red on the second disjoint, independent, or neither? Well, they're definitely not disjoint, because getting a red on the first and a red on the second should be possible, unless you have a very small bag with only one red M&M. Are they independent? Well, this is the subtlety, and I wish they would be more careful about this. They're independent if you draw with replacement, which seems pretty unlikely given that they're M&Ms and they're tempting to eat, or it's a really big bag, and you're essentially not affecting how many reds there are by drawing one out. Okay, if it's a small bag, this is important. If it's a small bag and you draw without replacement, without putting it back, then it's neither. Definitely not, still not disjoint, unless there's only one red, but they're not independent. Now, most of the time in statistics, we've got big populations, and you're drawing, and we're most interested in the case where you're sampling out of a big population. So in stats, most of the time, we're going to have sampling from a large population, and we're going to have some quantitative rules about that. And so we do assume independence. But it's really because we have a large population. So that really will come back to us.